बाकी लोग कहाँ है भाई? Am I audible?
यस सर।
बाकी लोग क्यों नहीं ज्वाइन किए अभी तक?
सर एक बार बोलता हूँ मैं।
बोलो, सब ज्वाइन करेंगे।
सर एक बार लेक्चर्स तो बचे हैं ना, वो आज अपलोड कर देना।
हाँ।
जो वीडियोस है ना लेक्चर वाले, वो आज अपलोड कर देना, मतलब आज तक के।
आवाज क्लियर नहीं है, फिर से बोलो।
सर जो वीडियोस है ना, वो अपलोड कर देना सर, लेक्चर्स।
उससे कुछ नहीं होता, आपको अटेंडेंस भी तो लगानी होती है। क्लास में नहीं आओगे तो कैसे काम चलेगा?
हाँ सर, तो इसलिए बच्चों को एक बार आप ये भी बोल दो कि
मैं
अटेंडेंस का
वीडियो
मांगता है ये सब।
वीडियो वीडियो अपलोड करना बंद कर दूंगा मैं फिर तुम लोगों की। फिर एग्जाम में सबके गलत होंगे आंसर। आपको क्लास में रहना जरूरी है भाई। इस तरह से कैसे इंजीनियरिंग करोगे? पार्ट टाइम इंजीनियरिंग नहीं होती है। नुकसान आप लोग का है अगर क्लास में ढंग से नहीं पढ़ोगे तो। So today we will start with the overall mechanical energy balance. Okay, so till last class we have studied the microscopic balance. So from today we will start with the macroscopic balance. So what is the difference between the microscopic balance and macroscopic balance? In microscopic balance, we will study the phenomena of fluid at a local point of the channel. Okay, so suppose the fluid is flowing inside a pipe. So at a local points, what is happened that we were studying in the microscopic balance. So suppose this is a point. So at this point, what is the velocity, what is the pressure, that you can calculate from the microscopic balance. Then you can average out it or you can integrate it for the overall system. Okay. So the basic problem with microscopic balance that the mathematics is slightly typical, as well as you cannot solve the problem for the easier. You cannot solve the problem very easily by for the turbulent flow. For the laminar flow, you can solve the problem easily, but for the turbulent flow, the problem becomes very much complicated. So for most of the times, because in industry, in the other purpose, generally the fluid flows in the turbulent region only. So we will use the macroscopic balance. So in the macroscopic balance, we will do the overall balance of the system. Instead of doing the microscopic balance at a local point, we will do the balance for the overall system. Okay. So suppose this is a pipeline, or we can make a slightly different diagram. Not horizontal pipeline, it is a inclined pipeline like this. This is point 1, this is point 2, Okay, so the velocity at the point 1 is v1. So here velocity means the average velocity, not the local velocity. So how to calculate v1? Suppose here the volumetric flow rate is q1. Here volumetric flow rate is q1 and the cross sectional area of the pipe is a1. So v1 equal to q1 divided by a1. Okay, so this is how you have to calculate the average velocity. So v1 is the average velocity at the middle of point. At the center of the circle, the velocity should be highest. At the walls, the velocity should be 0. In between, you have the parabolic function. Velocity varies as a parabolic function of the radius, but you can take the average velocity of v1 average. Okay, so this is the average velocity. It can be represent v1 average. Okay, similarly at the point 2, the average velocity of the fluid is v2 average. So this is again the average out the velocity to the whole cross sectional area. Okay, this is not a local point. Here pressure is P1, here pressure is P2. Okay, the elevation at this point, elevation is Z1 from the ground. This point elevation is Z2 from the ground. This is the elevation from the ground. Z1 and Z2, these are the difference between the ground height. Okay, P1 and P2 are the pressure. Now the density, suppose fluid is a non-compressible fluid and density is constant rho. This is a constant value of the density. Then you can use the Bernoulli equation to solve the problem. So what is the Bernoulli equation? In this case, so Bernoulli equation can be written as 1 by 2 alpha V2 square average, V2 average square minus V1 average square plus G in bracket Z2 minus Z1 plus P2 minus P1 divided by rho. Rho is the density plus summation of F. F are the friction losses, different type of friction losses, plus WS equal to 0. Okay, so this is the generalized Bernoulli equation. Okay, so basically this equation represents the energy balance for the system. Okay, so this is called the Bernoulli, generalized Bernoulli equation. For mechanical energy balance, here the assumption is, what are the basic assumption in the Bernoulli equation? First, your energy is not converting, mechanical energy is not converting in the thermal energy due to the simple causes. The density is constant, density is not varying. The second assumption. So these are the major assumptions in this equation. Okay, now here delta F is the friction losses. So due to the friction, here when you include the delta F are the friction losses. Okay, so due to the friction, some of the mechanical energy is converting in the thermal energy. So that friction losses may occur due to the different types of defects or different type of the geometrical structure of the flowing channel. So that we will discuss in detail. And that WS is the work done by the pump. Okay, so suppose there is a pump situated in between the line. So in this in between these 2 points, there is a pump which will converting the mechanical and the electrical energy or the mechanical energy to the pressure energy. So that will increase the overall mechanical energy of the fluid system. Okay, so you have to add the WF. Okay, so this is equal to 0. Okay, so this is the generalized equation. Now we will focus on the friction losses. What are the friction losses in the system? So here friction losses summation of F. Okay, so there are two different types of friction losses can be characterized or classified in the two different types. First is the major friction loss and second is the minor friction loss. Okay, so friction losses can be characterized as major friction loss and second is minor friction loss. Okay, so what are the difference between the major friction loss and minor friction loss? Basically, the major friction loss is due to the skin friction. So, what is the skin friction? Skin friction, nothing. We have already discussed about the skin friction during the derivation of the pipe flow, derivation of the pipe flow in the microscopic balance. So, basically, because the no slip boundary conditions, the fluid velocity is zero at the surface of the wall. Okay, solid wall. Okay, so inside the pipeline, due to the no slip boundary condition, the fluid velocity is zero at the surface of the walls here. Okay, and maximum at the center of the pipeline. So basically, due to the friction of the pipeline, there is a drag of the fluid which is flowing. Okay, so that is called that drag is called the skin friction. Okay, so this is the major loss in the system. So basically, due to the pipeline, due to the skin of the pipeline, which exerted the friction force on the flowing fluid, so there is a loss of mechanical energy into the thermal energy. That is called the friction, skin friction. Okay, so the major loss is also called the skin friction loss. Okay, now the minor losses include the different types of losses. So we will discuss what are the different type of losses in the minor losses. In minor losses, this is the major loss, skin friction. Skin friction loss. Then you have the minor losses. So they are different region or they are different categories of the minor losses. Okay, so minor loss, what are the conditions or what are the situations when the minor loss occur in the pipeline? Suppose first is when the flow direction is changing, है ना? First is when flow direction is changing. Okay, suppose you have the 90-degree bend in the flowing channel. Your pipeline suddenly moves in the 90 degree, or you have the 180 degree of you have the 360 degree of the U-turn. Suppose your the fluid is flowing in the 360-degree bend, or you have the 45 degree of turn. So these are the very common term, especially the 90-degree turn is very common turn in the hydraulic fittings, hydraulic systems. So whenever you have this type of change in flow direction, some of the energy will convert in the some of the mechanical energy will convert in the thermal energy. Why? Because due to the randomness, or due to the when you change the direction, some of the turbulence will created in the system. So that turbulence will convert the mechanical energy to the thermal energy. Okay, so this is a one type of minor loss which will occur in the system whenever you have the bend, or you are changing the direction of flow. Some of the energy will convert in the thermal energy will convert in the mechanical energy will convert in the thermal energy. Okay, so that is the one type of minor loss. The second, due to different type of fittings. So basically, pipe wall is very smooth wall, and in the pipe, now suppose there you are joined, the two pipes are joined together by using a type of fitting. Okay, so this is the joint between the two pipes. Okay, so is a type of gasket or flange which are using to join the two pipes. So because of this gasket, there is a friction in the flow. Okay, so this will create the extra friction because the pipeline is a smooth. Okay, but whenever this type of fitting will come, it will create the extra friction or extra disturbance in the flow. Okay, and due to this disturbance, some of the mechanical energy will convert in the thermal energy. Okay, so that will create the friction loss. That is the second type of minor loss due to the different types of fittings, which will preserve, which you have to include inside the hydraulic system. Okay, that will disturb the flow rate and create and convert some of the mechanical energy to the thermal energy. The third type, whenever you have the enlargement or the reduction of the pipe diameter. Okay, so suppose you have a pipe diameter like this. This is the big pipe. Then again, suddenly it will joined with a small pipe. Okay, you are changing the pipe diameter. So whenever you do change the diameter, some of the mechanical energy will convert in the thermal energy due to due to the disturbance created due to the change of the velocity of the fluid. And due to this, some of the energy will convert in the mechanical energy, thermal energy, and you have the friction loss. That is called the enlargement friction loss. Similarly, this is the reduction, and similarly, you also have the enlargement. Suppose this is a small pipe, and again, this small pipe is joined with a bigger pipe. Okay, so fluid is flowing in this direction. In this case, fluid is flowing in this direction. So this is the reduction. This is the enlargement of the flow. So whenever you change the pipe diameter, there is a loss of the energy, and that is also also created the minor losses. So majorly minor losses occurs due to whenever you change the direction of flow, whenever any type of fitting present in the system, or whenever you change the diameter of pipeline. So these three are the cause of the major cause of the minor losses. And the major losses occurs due to the friction, skin friction. So skin friction is nothing but because the solid wall of the pipeline is in present in the stationary condition, so that will drag the flowing fluid, and so that will exerted a drag force on the flowing fluid. So this is a type of friction that is called the skin friction. It will convert some of the mechanical energy in the thermal energy. So that will the, and how to measure the conversion of the mechanical energy in the thermal energy. In every cases, in the flowing system, the mechanical energy represented by the pressure energy. Okay, so you will find the pressure loss. Suppose you are taking a horizontal pipeline. So in the horizontal pipeline, if fluid is flowing from one point to the other point, so the pressure loss should be based on the microscopic balance which you have calculated. Suppose here pressure is P1, here pressure is P2. So the pressure loss should be according to the Hausen-Fossley equation, and which you have developed based on the microscopic balance. But whenever you have the friction loss, so it will create the so whenever you have the friction loss, so it will create the extra pressure drop inside the system. Okay, so theoretically you will find the how you will based on the material which you have used and based on the flowing channel of the flowing characteristic, like it is a laminar flow or turbulent flow or other thing. Okay, so based on that you can determine at which range your flow is present. Okay. So now the next task is to calculation of the pressure loss due to the system, due to the major and minor friction losses. Okay, so the major and minor friction losses, skin friction loss, or the other type of losses. Okay, so you have to calculate how the overall pressure loss or the friction loss in the system. Basically, you have to calculate delta F, sigma F. So sigma F is the summation of major loss plus minor losses. So first we will calculate the major losses or skin friction losses. Okay, so we have already done this derivation before during the microscopic balance, so we will just repeating the same thing. For calculation of the major losses, you have to define a factor that is called the friction factor. Okay, so major loss is calculated based on the friction factor. And how the friction factor is defined, we had done this after the derivation of the pipe flow problem in the Newtonian fluid. Friction factor is defined as a tau W divided by 1 by 2 rho V average square. Okay, so where this is the ratio of the friction factor is a dimensionless number which provide idea about the magnitude of the shear stress. Okay, so how much friction is calculated. Shear stress is nothing but the friction. Okay, it is defined as the ratio of the shear stress at the wall and the kinetic energy, to the overall kinetic energy of the fluid. Okay, So friction factor is the ratio of shear stress. Shear stress is nothing but the shear force or the friction force at the wall. Shear stress at the wall and the kinetic energy of the fluid. Okay, so tau W can be written as tau W equal to minus in bracket minus tau RZ at R equal to capital R. For pipe flow problem, you remember this formula. We had done this experiment we have solved this before. So tau RZ, for tau RZ you need the Vz. So Vz velocity equal to Vz max in bracket 1 minus R square by 1 minus R square, small r square by capital R square. Okay, now just calculate dvz by dr at R equal to R. At R equal to capital R, you will get minus 2 Vz max divided by R. Okay, now you have to calculate the shear stress value. Okay, so shear stress considered as a momentum flux, that is written as shear stress value can be written as dvz by tau rz at R equal, small r equal to capital R, that is equal to minus mu dvz by dr at R equal to capital R. Now substitute the value from this equation. Suppose this is equation number 1. Substitute the value from equation number 1. You will get that equal to plus 2 mu Vz average, Vz max divided by capital R. That is the tau WR. Okay. Now you can substitute the value of Vz max from the original equation. You will get in terms of the pressure difference. So that is that we had done before. So when you substitute the tau W equal to tau RZ at R equal to capital R, that is equal to 2 mu Vz max divided by R. Now substitute the value of the Vz max from the equation. So it is equal to P naught minus PL, that is the pressure difference across the pipe. P naught minus PL multiplied by R square divided by 4 mu L. And this R will remain same. So this R will be cancelled out. 2 will be cancelled out from here. It will remain 2. Mu will be cancelled out. So you will get P naught minus PL divided by 2L multiplied by R. This is the value of tau W. Okay. Now you have to calculate, you have to just substitute the value in the original equation. So when you substitute the value in the original equation, you will get F equal to friction factor equal to tau W divided by 1 by 2 rho V Z average square. Okay, now substitute the value of tau w from the previous section. That is P naught minus Pn multiply by R divided by 2n divide by 1 by 2 rho Vz average. 1 Vz average will remain same, and instead of 1 multiply by Vz average. Okay, now this Vz average you have to substitute value of the 1 Vz average in terms of pressure. Okay, so that this pressure will be cancelled out. Okay, so because this is a dimensionless number, we are trying to develop some correlation based on the Reynolds number. Okay, so we have to substitute the value of Vz average here. So P naught minus Pn divided by 2n R divided by 1 by 2 rho Vz average multiply by value of the Vz average. So Vz average can be written as P naught minus Pn divided by 8 mu L multiply by R square. Okay, now the values will be cancelled out. This L will be cancelled out. This R will be cancelled out. This P naught minus Pn will be cancelled out. Okay, so you will get this 2 will be cancelled out again. So you will get 8 mu divided by rho R V average. Okay, now you can convert R in the diameter D. So it will equal to Fanning friction factor equal to 16 by rho R, not R, rho D V by mu. Rho D V average divided by mu. So this quantity will become Reynolds number. You will get 16 by NRE, Reynolds number. So this is the value of the friction factor for the laminar fluids. Okay, so that is the simple friction factor. There is one more term that is called the Fanning friction factor. Okay, so there is a small difference between the simple friction factor and the Fanning friction factor. In the Fanning friction factor, this is the friction factor for laminar flow. So you have the Fanning friction factor, which is developed by the scientist Fanning. So in Fanning friction factor, F is defined as not 16, 64 divided by NRE. Okay, so that is only difference. Okay, so basically the Fanning friction factor is equal to the 4 times of the friction factor. Okay, so the instead of 16 we are using the 64, that is the Fanning friction factor. Okay, so both are the same thing, only the difference is the calculation. Okay, so this is the 64 divided by NRE, Fanning friction factor. Okay, now this is for the turbulent flow, this is for the laminar flow. If you have the turbulent flow, if you have the turbulent flow, then the calculation will be totally different. So how you calculate in the turbulent flow? In the turbulent flow, the value of the friction factor or the Fanning friction factor will depend upon the Reynolds number as well as the surface friction or surface that is called the surface roughness. Okay, so roughness factor. It will depend upon the roughness factor of the pipeline as well as the Reynolds number. Okay, so for turbulent flow, suppose this is a pipeline. So when you enlarge this area, you will find that this is like, this area is basically the rough enough. Okay, so this roughness factor will incorporate in the friction in the turbulent flow. Okay, so how you calculate the roughness factor? The roughness factor equal to the thickness of the roughness, that is called the xi, divided by diameter of the pipeline, that is calculated from the d. So xi by d is the roughness factor. So once you know the roughness factor, you can use the Moody's chart. Okay, so Moody's chart are the standard charts which are used to calculate the friction factor in the turbulent flow region. Okay, so this is the log graphs. So these charts are available with in the books also, in the data books, different data books of the fluid mechanics. In every book of fluid mechanics, you will find the Moody's chart. So x-axis you have the Reynolds number, which is also in the logarithmic scale. Like this. Now in y-axis you have the Reynolds number, you have the friction factor F, which is also in the logarithmic scale. So basically this number, this graph represents the correlation between the two friction dimensionless numbers. One is the friction factor, second is the Reynolds number. Now in the laminar region, you have the straight line like this. So this point is suppose 2100 Reynolds number. Again, after this line, you don't have any straight line. Okay, so this straight line represents the 64 by NRE for the ferry friction factor, or 16 by NRE for the simple friction factor. After this, you have the different curves like this. So every curve represents the a surface roughness factor. Okay, so suppose this represents the psi by d equal to 0.03. This represents the psi by d equal to 0.0003. This represents the psi by d equal to 0.0001. This represents the psi by d equal to almost 0, means smooth pipes or tubes. Okay, so in this way you have the more than 10 lines, 15 lines, based on the how much big graph you are using. You have the more lines, more accurate results you can predict. Okay, so what you have to do, first calculate the Reynolds number of fluid based on the velocity, based on the density, viscosity and diameter of pipeline. First calculate the Reynolds number, then calculate the roughness factor. Generally it is given in the problem based on the material you are using. The roughness factor is fixed. Suppose you are using a pipeline which has the roughness factor 0.03 and you are working in the one leg Reynolds number range. So just go to one leg to the this point, roughness factor 0.03, then move in the horizontal direction. You will get the value of the friction factor. Okay, so once you know the value of the friction factor, you can calculate the pressure loss due to the friction factor. Okay, so in this way this term will use. Okay, now this is about the Moody's chart. Similarly, you might have the different type of correlation also. Okay, so there are different type of correlations which are also available to calculate the loss of the flow due to the friction. Okay, so you might have the different type of losses due to the different categories. So how to correlate the pressure loss to the friction factor? So there is a simple formula. So delta P by rho, the loss due to the pressure loss due to the friction factor, that can be calculated by delta P by F. So friction loss, skin friction loss can be represented by capital F, small f as a subscript. That is equal to delta PF. This is the pressure drop divided by rho. Rho is the density. That is equal to 4 multiplied by F. F is the fanning friction factor. Multiplied by delta L divided by D. Delta L by D is the ratio of the length by diameter. Multiplied by V square divided by 2. This is the pressure loss due to the friction factor, or you can rearrange this equation little bit. So you will get delta P by L, pressure drop per unit length, that is equal to 4F multiplied by rho divided by D multiplied by V square by 2. So this formula is more famous. Okay, so always you are calculating the pressure loss per unit length. Okay, so that can be calculated from this formula. So you know, if you first you have to calculate the velocity, then you have to calculate the Reynolds number. Once you know the Reynolds number, use Moody's chart. If it is a turbulent flow, you can use the Moody's chart. If it is in the laminar flow, you can directly use 64 by NRE to calculate the friction factor. Once you know the friction factor, just substitute the value of the friction factor F in this equation. Here V is again the velocity, rho by D is the density and the diameter of the pipeline. You can calculate delta P by L. Delta P by L means the pressure drop per unit length due to the friction, skin friction losses. Okay. So from here you can calculate the loss, major loss from the equation, from the in the pipeline. Okay. Then you have the minor losses. So friction loss in expansion, contraction, and pipe fitting. These three are the minor losses. the friction losses due to the expansion contraction of the pipe fitting. Okay, so first we will see how to calculate the friction loss due to the sudden enlargement or expansion of the pipe. So sudden enlargement or the expansion of the flowing channel. Okay. So whenever you have the sudden enlargement of the flowing channel, the friction loss can be calculated as suppose I am making a diagram so you can understand better. This is the enlargement. Fluid is flowing in this direction. So here the cross-sectional area of pipeline here is A1. This is the cross-sectional area of pipeline. The velocity is V1 here. Here cross-sectional area will become A2. Here the area is become A2. Okay. Now the friction loss can be calculated as HEX equal to in bracket 1 minus A1 square A1 by A2 square bracket close square multiply by V1 square divided by 2 alpha. This alpha I will explain what is this alpha. Okay. Now this can be represented by KEX V1 square by 2 alpha. Okay, then the unit is joules per kg. Okay, now this is the friction loss due to the sudden enlargement. Okay, so where KEX equal to, this is the friction loss factor in this case, and friction loss factor is equal to 1 minus A1 by A2 whole square. This is the friction loss factor. Okay. Similarly, if you have the sudden contraction in the cross-sectional area of flowing system, okay, in this case you can write He equal to 0.55 multiply by in bracket 1 minus A2 divided by A1 bracket close V2 square divided by 2 alpha. Okay, so this is the friction factor due to the sudden contraction. Okay, so here you can write Kc equal to 0.55 multiply by 1 minus A2 square divided by A1. A2 by not A2 square, A2 by A1. Bracket close. Okay, so this is the sudden contraction factor. Okay, Here the velocity is the downstream velocity. So basically this is the sudden contraction. This looks like this. Now here V2 is the velocity in the downward direction. This is the V2. Okay, at this point here your surface area is A1. This is A1. Here the cross-sectional area is A2. Okay, the velocity at the downward stream is V2. Okay, so here the velocity is in the upward stream, that you have to remember. In this case the velocity is in the downward stream. Okay, so both are the different positions. Okay, so these are the loss due to the sudden contraction. Okay, now you have the different type of loss due to the different type of fittings and walls. Okay, so there is a table which is given in the book. Okay, so I am writing some of the major values, and you can find other values in that table, or in the exam it is given to you what are the friction losses due to the different types of fittings, or when the flow is changing, the direction of flow is changing. Okay, so this is the table for minor losses due to different types of fittings. Okay, so first is elbow. Elbow is used for the changing the direction of flow. Okay, so 45-degree elbow. So 45-degree elbow will change the direction in the 45-degree. Elbow 45-degree. So the value of Kf, minor loss factor, friction factor, that is equal to 0.35. Second is elbow 90-degree. The value is 0.75. Kf value is 0.75. Then the T is used to change the flow in the two direction. Okay, so basically T is basically this type of channel where this is the inlet and this is the two outlets. You know? So when you convert the flow in the when you divided the flow in the two different channels. Okay, so the value of Kf is 1. Then the couplings are used to join the two pipes, coupling and unions. So coupling and unions. So these are basically the smooth joints. So you have the Kf value 0.04. Now fifth is gate wall. So gate wall might be the full open or the half open. So if you have the full open gate wall, at that time the value is 0.17. If you have the half open gate wall, the value is 4.5. Similarly, sixth, the globe wall. Globe wall has the similar purpose as the gate wall to start and stop the flow. It can slightly regulate the flow also. So you have the full open globe wall and the half open globe wall. The values are 0. If the full open globe wall values are 0.6.0, and for half open globe wall values are 9.5. So this globe wall create a lot of pressure drop. Then you have the angle wall wide open. The value of Kf is 2.0. Then you have the check walls. So check walls, ball type check walls and the swing type check wall. The ball type check wall has the value of 70, which is very high. So pressure loss in the ball type check walls are very high. Then swing type check walls. In the swing type check walls, the value is 2.0, which is quite low. Okay, then you have the water meter disk. So if the water meter disk is present in the system, then the value of Kf is 7. So for water meter disk, the value is 7.0. Okay, so these are the value of the friction coefficient for different Kf friction coefficient for different type of minor losses. Okay, so suppose in your pipeline you have the two elbows, one T, one gate wall. So you have to just add all the values and you have to take the all the values and multiply with v square by 2. Okay, the friction factor. So basically in this formula you will find that this is the Kc. Kc is multiplied by v square by 2 alpha. So here also you have to just take the values and multiply with the v square by 2. That you will get the exact answer. Okay, so now we can write the summation of all errors. Okay, so summation of all errors can be written as sigma f, that should be equal to, in bracket, 4 multiplied by f. F is the fanning friction factor, which you can calculate from the Moody's graph, divided by delta L by D. Delta is the length of the pipeline, D is the diameter of the pipeline, plus Kex, the friction factor due to the expansion, plus Kc, the friction factor due to the contraction, plus Kf, friction factors due to the Kf1 plus Kf2, friction factor due to the dash up to the plus Kfn. These are the friction factor due to the fittings multiplied by v square by 2 alpha. Okay, so these are the value of sigma f, total loss of the pressure due to the different type of fittings, walls, as well as the pipelines. Okay, so whatever the solid boundaries are present in the direction of the flowing fluid and in the place of the flowing fluid, so that will create a type of friction, and that friction can be calculated from this formula. So this is the pressure loss. Okay, in the system. Now what is the alpha in this case? Okay, so you can find in the original equation also, but the equation we use the term alpha. Here again, here we also use the term alpha. Okay, so alpha is a correction factor. Okay, if the value of alpha is not given in the problem, then for laminar flow, alpha equal to 0.5, and for turbulent flow, alpha is almost equal to, nearly equal to 1. Okay, it is like 0.95 or 0.96 also sometimes. So if the value of alpha is not given in the problem, you can use for laminar flow alpha equal to 0.5, and for turbulent flow alpha is 1. So what is alpha? Basically, kinetic energy should be calculated at the local point. Okay, so what we are doing, suppose this is the pipeline. So at the center of the pipeline, the velocity is maximum. At the boundary, velocity is 0. So when you are calculating the kinetic energy, V1, suppose at the center of the pipeline velocity is V1. At the boundary, it is like V infinite, which is nearly equal to 0, V0, which is nearly equal to 0. So what you are doing, you are calculating the V1 square, V0 square, and similarly in between points, you are calculating the kinetic energy at every point, and then you are taking the surface integral of the kinetic energy, and then you are doing the average out, and basically you are average outing the kinetic energy. So here, for taking the, you are taking the average of the velocity square. So there is a correction factor which should come, and whenever you are doing the average out a quantity, and that is also a square of some other quantity, so you have to take a correction factor. So these are the correction factor. So there is a thumb rule: for the laminar flow it is 0.5, for turbulent flow it is nearly equal to 1. Okay, so you have to use this correction factor alpha. Okay, you have to remind the correction factor come in the sigma f as well as in the kinetic energy. Okay, here as again and here again. Sigma f can be calculated from this formula. Okay, so this is the formula of sigma f. So it is the summation of the skin friction factor due to the sudden expansion, friction factor due to the sudden contraction, then the friction factors due to the different type of fittings present in the system, multiply by v square velocity divided by 2 alpha. Okay, you will get the sigma f. Once you know the sigma f, you can calculate the overall power requirement in the pump. W is the power requirement in the pump. Okay, so once you know the all values, you can calculate how much, what should be the size of the pump. It is 1 horsepower, 2 horsepower, 5 horsepower. What should be the size of the pump? This is the power requirement in power. Again, when you calculate the power requirement from the Bernoulli equation, this equation shows you the theoretical power requirement. Okay, so actually pump has its efficiency. So the efficiencies of pumps are generally the 0.8, 80%. So it will convert the 80% of the electrical energy in the mechanical energy. Okay, generally pumps has the efficiency of the 80%. They converted the 80% of the electrical energy in the mechanical energy. So if your power requirement is the 2 horsepower, so you have to divide 2 horsepower divided by 0.8. You will get the actual size of pump. And now what should be the actual size of the pump? Okay, so in this way you can calculate what should be the size of pump. Okay, so we will solve the problem in next few classes related to this derivation. ठीक है, समझ में आ गया आपको?
यस सर, यहाँ तक तो
Yes,
आ गया
sir.
सर।
ठीक है, इजी है,
Yes.
ज्यादा टफ नहीं है. नाउ वी विल सॉल्व सम न्यूमेरिकल प्रॉब्लम, है ना, नेक्स्ट क्लास से सॉल्व करते हैं. ठीक है. और दिस इज फ्रॉम द जिंकोब्लिश बुक. आई थिंक आई हैव शेयर्ड विद यू द जिंकोब्लिश बुक. मैं चेक कर लेता हूँ शेयर किए कि नहीं किया. There are two books which I am following. First is the here I have shared on the 7th January. First is the McCabe-Smith unit operations, and second is the transport processes and the unit operations. That is from the Jinkoblish. So दोनों बुक में मिल जाएगा आपको ये वाला पार्ट. Jinkoblish में ज्यादा अच्छे से दिया हुआ है. Okay, so if you want to follow even the numerical which we will solve in the classroom, that will from the Jinkoblish book. They have the much more numericals related to this topic. Okay, so we will follow the Jinkoblish book for this topic. ठीक है, नेक्स्ट क्लास से कुछ न्यूमेरिकल सॉल्व करते हैं.
ओके सर.
हाँ, किसी कुछ पूछना है? और
No, sir.
चलो ठीक है.